There was a promise in the first lecture that at the end you should see atoms. I hope we can meet that promise. But in a way, it will depend on how much you now know, because we shall have to show you atoms at the very end of this lecture by an indirect method. You must know now there's no hope of seeing them directly. And at the same time, we shall be using models to help you to understand how it is that at long last you see atoms. I want to go back to the question of safety of nuclear material. First of all, look at the half-lives of the things that you have had dealing with. First of all, a very short half-life. The half-life of the granddaughter of uranium was so short, it was, say, 1.25 minutes. You saw it even measured. What's going to happen after an hour? It's had perhaps 40 half-lives. In 10 half-lives, it drops down to 1,000th of the original population of those nuclei. In 20 half-lives, to 1,000th of a thousandth, a millionth. And that's only after 20 half-lives. And I should think it goes on for something like 40 half-lives in an hour. And so it goes down to 1,000th of 1,000th of 1,000th of what there was originally, and I really wouldn't worry about it. Meanwhile, all that's happened very fast, so that if you had 1 million atoms near you, any damage it could possibly do would be done in a short time. That's why we don't worry about disposing of that. But, Dr. Evans, what did you use for the tomato plant?
We used phosphorus-32 with a half-life of about 14 days.
2 weeks. 2 weeks, 26 lots of 2 weeks, even if that only went down by 20 lots of 2 weeks. That's 20 half-lives down to 1,000th of a thousandth, 1 millionth. All you have to do with the phosphorus is to store it somewhere where nobody's likely to touch it, go near it, or burgle it, and after that there's very little left indeed. What about your gamma-ray source that you came outside and it came into your counter?
Well, that was much longer. That was cesium-137 with a half-life of about 30 years.
30 years, a good fraction of a human life. That's going to be much more difficult to keep safely while it slowly wastes away into a curious and not very long life product. Where does it come from?
Well, that's a fission product, cesium.
You mean it's not ordinary cesium?
No, it's not ordinary
Please don't be afraid of a cesium compound in the chemistry lab. It's a fission product. It's one of the fragments that comes out when a uranium nucleus breaks up. It only happens sometimes with that particular one. I'm going to remind you about a bomb again. Please don't think I like nuclear bombs, but what I dislike just as much is ignorance. It's very dangerous to argue about dangers without knowing what they are. And so we do explain about a bomb, the need for critical size, the idea that you must not only have a big chunk of uranium, but you must have it with neutrons given out, which will fly, not to escape if it's big enough, and which will set off more fissions. And so you have more and more and more like the mousetrap model. At the same time, each fission releases an enormous amount of energy. I'd like to remind you, with my uranium nucleus of the Royal Institutions Museum, which is here, and when fission occurs, in goes a neutron. Those are neutrons, the little black fellows in our way of painting them. When a neutron goes in, this vibrates a little, and then suddenly, oh look, 3 neutrons to spare. Out they come, possibly a little late, and they can start more fission for you. You can have a chain reaction. These are fission fragments, unequal halves of the nucleus. I'm going to leave that there for a moment because I want to be able to show you a picture of that happening. We're going to put that on one side. This is a picture of a uranium nucleus which has received a neutron here, and it takes it in and keeps it in and becomes a different uranium, and then it begins to oscillate. It vibrates like that and vibrates like that, different ways, until finally it begins to pull apart with a waste forming here, and those 2 fragments fly apart with enormous energy. If you think in terms of electron volts, a slightly outdated version of an energy unit, but a very useful one, a carbon atom burning delivers 4 electron volts of heat. A uranium atom undergoing fission delivers nearly 200 million instead of those 4 electron volts of heat. An enormous amount of heat, great burning heat, dangerous to people, but useful if you can tame it in a reactor. So much for that picture. I'm going soon to talk about a reactor, and therefore I'm going to show you a very ancient picture of a reactor, which will be an easy way of thinking about a nuclear power station. It's a great block of something with cooling arrangements going in and out, and the uranium used has to be taken out and put into a chemical separation plant to get what uranium is left over separated from something else. It's watched by television from outside. It's a nasty creature, so it's well shielded. Here is a picture again of a reactor with a wasp or bee storm of neutrons inside. You could hang some phosphorus in there and or another suitable element neighbor of phosphorus and manufacture radioactive phosphorus by hanging it in a reactor. Just to remind you of the same thing that happened with silver, neutrons don't stick in a silver nucleus unless they're moving slowly. They crawl in and then get welcomed. And so here is a source of neutrons, and we get a neutron coming out and bang against a hydrogen nucleus in the water here of the moderator. So it's slower and slower and slower and zigzag, zigzag, zigzag. It's very slowly now. It's going at about the speed when silver will grab it. That zigzag is something to keep in mind. That's making the neutrons of the sort of speed and energy of air molecules in this room. So that we have, with a reactor, which we are now coming to, uranium atoms delivering the energy of hurling each other apart, the 2 fission fragments, making an enormous amount of heat. Before we talk more about reactors, I want to talk to you about one matter, apart from the safety of reactors and dangers of reactors, but it's a matter of our own welcome to you here. We welcome you to see experiments that you should see, that you would enjoy, that will be useful. But our experiments are, many of them, special ones. They're specially put together by expert people and watched by expert eyes and hands, I don't mean mine, to make sure that they are being run in a proper way. Most of our experiments, therefore, are special ones here to help you to understand and to enjoy. They are not ones, therefore, to try at home. I'm sorry, but most of our experiments have a very serious wish that goes with them. Do not try them at home. They could be quite unsuitable for home use. I've said that before in other words, but I think it's probably wise to say it once more. We want you to see these experiments because they're there to add to your wisdom. And wisdom is very valuable. Some of them, of course, are not like that. There are experiments that you could easily do at home, such as blowing a soap bubble or putting an oil drop on a tray of water. Those are straightforward, and we say so. But unless we say so, please remember that our experiments are very special, and the people arranging them here have special skills for seeing that they go well and they're not in any trouble to you. There's both my apology and my blessing. I would like to show you now some things concerning safety and reactors, and I've talked about reactors without explaining what they are. So we will put this, which we finished with, out of the way, and I'm going to talk on the screen about a reactor for a short time. In a reactor, we have a big block. It's got to be bigger than critical size, but then reduced by cadmium rods or rods of a similar replacement to keep it disciplined. And in the reactor, we're going to have uranium-235, that will do fission, and uranium-238, which does not so easily do fission, and so out will come neutrons from that, zigzagging round inside this material, which we call the moderator. It's carbon very often, possibly heavy water, and some material to make it go slower. Now what happens? The neutron that's released by this may hit another 235. Here's a 235 that just caught it before this neutron managed to escape. It was going to escape out there, but it didn't. And so this keeps the action going. Meanwhile, this one may hit 238, and it is gobbled up. It does not come out. Various strange things will then happen there. You will see the 238 turn into 239, and then it gives out something, becomes another new unknown element, and that in turn gives out something and becomes a new unknown element. And I would like to show that to you for the fate inside this with a slide. I'd like the blue slide, please. Here is a U-238. It gains a neutron and then becomes U-239, which is not stable. It's radioactive, gives out a beta ray, a fast electron. In the course of time becomes Neptunium, named for an astronomical reason, 239. Another beta given out by that in long due course becomes a new element, again astronomically known, plutonium. I'm very sorry that plutonium should be regarded as such a dirty word. It's practically a swear word in certain journals and elsewhere. Please understand that it is just one of the chemical elements, and a lot of them are not good to eat. The use of plutonium is very important. Your great-grandchildren may depend upon it. We'll see why in a moment. If you kept plutonium for long enough, it would give out an alpha particle, and of all things would give you U-235, but you wouldn't wait for that, because we can put plutonium to a different use in a reactor. I want to go back now to my picture on the screen and talk about using plutonium inside a reactor. Here it is. Here's my reactor, and I'm going to have now added some plutonium. This is going to be a faster reactor in one way. I don't mean that it suddenly goes whoosh like that very quickly. I only mean it's going to make use of fast neutrons. There'll be some 235. there will be a lot of U-238 because it's the common uranium. And when a neutron comes out, it may go into plutonium. And if it does, it will produce fission and heat. And so we'll just give a symbol of that. There'll be fission heat coming out there. There'll also be fission heat coming out there. If it goes into plutonium, that could happen. But what happens when it goes into 238? Neutrons from the plutonium fission or from the 235 fission can go into 238, and in due course you will get more plutonium. And so that is why we call it a breeder. It breeds more plutonium, and it can make use of fast neutrons without needing so much moderator. And it doesn't mean a whiz-bang whoosh affair. It only means something which can use fast neutrons and use up the enormous store which we have, useless otherwise, of the wrong uranium. And that's why we can gain, by what kind of factor would you say, Dr. Evans?
Quite a large factor. You ought to get about 90% of the available energy out of the uranium by
90% of the uranium, yes, instead of?
Or round about 5% of the energy.
90% instead of 5%. Would you like to be paid 5% of your wages or 90%? It's an enormous difference. And that will be something that you will meet. I would like to show you two things that Dr. Evans has brought. One is a slide, admittedly simplified picture, because this gives you a feeling for what a reactor is like, and you're going to see a real model very soon. An outside shield, that's very important. You can hardly drive your ordinary car with a nuclear reactor because the concrete shield will break up the tires even. Inside that, there are rods of fuel, which are shown red here, shown in color, and there are control rods to keep the thing disciplined so that one fission leads to one fission, leads to one fission, like our long single row of matches. And all through that, there is moderator to slow neutrons down for the simple type of reactor, and there is a cooling system which we haven't even shown. We'll come back to that. Now let's deal with dangers and troubles, please. Let me see the arrangement for taking nuclear material from a reactor home to be reprocessed and separated chemically. There it is. This is a railway car taking nuclear waste away. Dr. Evans, how big is it?
It's about 50 tons, and as you can see, it's ribbed to give cooling. It's made of steel.
Well, why cooling?
Because you generate a fair amount of heat from the fuel because it is so radioactive.
It's just normal alpha particles and other mess coming out.
Yes, mainly fission products.
How safe is it? Could it be burgled?
You'd have a job to burgle it because you'd have to undo a large number of big bolts on top. You could also drop it down a 30-foot railway embankment into a burning pool of petrol and it still would survive, completely intact.
Is that a standard test?
No, it isn't, but they do test them. They test one.
But it has been done?
It has been done.
Good. It seems to me unburglarable and a very difficult creature to hijack. What would happen if it were hijacked?
Well, if anyone took the lid off it in conditions which weren't very carefully controlled, yes.
I'd like to see another picture. No, you don't have it. It's in Dr. Evans's pocket, isn't it? This is a very strange thing. This is a block of glass. Quite heavy. It's brown glass. It's a model only in the sense it does not have radioactive waste embedded in it. There is now going to be a process of safeguarding radioactive waste by glassification, by turning it into a glass blob like this. Except that this is not radioactive, this is the size of a chunk of glass that will hold all the radioactive waste from a power station which has supplied one human being with all the electrical energy he needs in his whole lifetime. One man lifetime's use of radioactive nuclear fuel. The remaining stuff that's left over can be put in a piece of glass that size. This is perfectly safe because the fuel remains have not been put in, but that is the size. Thank you very much for bringing it for people to see.
You might like to know that if the equivalent amount of coal were used, then we would have a pile of ash about the area of this and around 15 feet deep.
Yes, you gave me, when we were chatting about it, some dimensions of the ash in a block.
But it works out to be about this area and about 15 feet deep.
15 feet deep or high.
Instead of that.
Instead of that. Oh, you mean the area of the round thing?
Yes.
Yeah. Great pillar of it, of ash. This is a much more economical thing in size. We are going to show you now a model of a reactor, which is just a thing that uses fission for a power station. And the model will come in two parts by two ways. First, a scale model. The scale model, Mr. Coates will turn it round so people get a glimpse directly. And here behind me, the model is going to be an illuminated scheme to show how it works. This is a model of a reactor which is not yet in full use. It's being manufactured to be put in 1981 at new power stations. And each of these such reactors, there's the scale model, here's the diagram of it, each of those will actually provide in electrical power about 500 million watts. 500 million watts. Now let's look at this. It's the total power station will generate something like 1,000 million watts, because it'll have two of these. In this one first, you can see that we are pumping carbon dioxide gas down there, in at the bottom, up through the middle region, out of the top, down again. It's circulating round there. It might become radioactive by picking up some particular nuclei, and therefore you keep it circulating in the whole show. It, however, goes through a heat exchanger, which is simply a boiler in which this zigzag thing carries water, which can be boiled into steam and can go out to run the turbines in the power station. And so you exchange from hot, very hot carbon dioxide to boiling steam, which can be used on both sides. Meanwhile, over here, we have the actual model. In the actual model, these dark things here, vertical things, are uranium and carbon. You can see here carbon, black graphite there to slow down neutrons so it goes into the rarer uranium and delivers fission, which keeps going at a regular rate, not an explosive rate. Here is an internal uranium rod, and Mr. Coates here has a real uranium fuel element, not from that type of machine, but from a somewhat similar one. This was never radioactive, it was never filled with uranium. It is just a sample which can be looked at to see what it would look like. Here we have pumps to circulate. Here we have the heat exchanger region explained by my curious diagram over there. Look at this for size. There's a man. Down there is a man between my two fingers. So that's 5 or 6 feet there, and this is an enormous creature. Look at the amount of concrete shielding. I think you have no idea of the amount of care, trouble, precautions, and skill that have gone into every such reactor to make it safe. You read of a disaster, just as you read of an aeroplane or traffic disaster, but one does not realize how rare those are compared to the enormous amount of care. But it's a new technology. It does have teething trouble sometimes. So that this is a model of an ordinary type of reactor, not, I should think, a breeder. It uses carbon dioxide gas as the cooling, and the cooling in turn carries the heat out to the power station. Those can now go away. I'm very grateful to the Atomic Energy authorities for lending them to us. They now go back to the great exhibition which will reopen in Edinburgh very soon. They've been brought here specially for you. I'm now going to show you what will look like a piece of school teaching. And I don't want you to think of it like that. This is a very important exhibit. It's a diagram, it's a graph, but of something extremely important. We're going to go back to that model of mine. May I have it either half or whole? We can call these red things hydrogen nuclei, but since it's the most primitive nucleus, of which all other nuclei are partly composed, we call it a proton. Proton means primitive, head, simple. And so the red things are called protons. They're hydrogen positive charged without its one electron. The black things are neutrons and have no charge, and they can sneak in and make a sneak raid, as I've told you, on another nucleus. Incidentally, the rest of the atom of this size is out in Piccadilly Circus, or further, Trafalgar Square probably. The two of those things, both the red and the black, can be called by one word, nucleons. They're about the same mass each, and we lump them together as constituents. Those are the constituents of a nucleus. This nucleus of uranium has 230 or 40 nucleons, combined number of adding the total of those two. Now here's a very strange graph. Along the number of nucleons in a nucleus, 235 in U-235, rather less, about 200 in lead, still less, about 50 in nickel and iron, still less in chlorine, very much less in lithium, light metal, only 6 in one of the heliums, 3 and another one, 4. And here are hydrogen and protons and neutrons themselves, right up there. These upwards are plots of the energy stored in the complete nucleus in units of 1/10 millionth of a joule, but only after you've divided by the number of protons and neutrons divided by the number of nucleons. This is the energy stored per nucleon, just like the price of oranges per orange. And so you take a dozen oranges, pay the money, and divide by 12 to find the price per orange. Here's the price per nucleon in stored energy. Now, why is this graph important? Look what it can tell you for power reactors. We're going to move in a new story. From U-235, we could go to two pieces down here at the bottom of the curve and get that amount of energy released in fission. That much tells you the fission release, because, going back again, if you don't mind, from any atom you like to take, it doesn't matter which, we've taken a nitrogen atom there, this whole distance right up to there is what it would cost to take the nucleus apart. Take this proton out, hold it up the stairs there, this neutron away, hold it up there against some nuclear forces, this one against some other nuclear forces, get them all out to pieces so the whole thing is all in onesies of those. That is the tear-apart energy. I beg your pardon, I showed you the wrong one. I'm so sorry. We're coming back to that. That's a secret. Forget you saw it. I want to put now the other one on top, if I may. Here it is. We have to take this diagram to pieces on the table, so it's difficult. That's better. From there, right apart from krypton, right up to there, is what it costs to tear that nucleus apart into these simple components. That's the tear-apart energy. But now look at the fission release on top of that. You see, uranium has less tear-apart energy. It comes to pieces more easily. And so that's why you get that much released when there's fission. And it's that part which is the fission release. But now I want you to look at something else. Remember, that's the tear-apart. I'm sorry I mixed it. Here is another part of the story. Here is from neutron and hydrogen and another hydrogen and lithium and helium, all quite light things. What happens if we start up there and come down to there? We're not doing fission, separating. We're doing fusion together. If we can drive some light things together, we can get enormous energy out. It isn't, to look at it, quite so big as uranium, because these things have a very few nucleons, and these are all a plot of energy stored for each nucleon. But still we would get a great deal of energy out, far more than burning coal or anything, and we can get these materials from the ocean in an almost unlimited supply. I consider it would be ignorant and wicked to discuss the future of nuclear energy without understanding that the hope of the future is fusion yield, not fission. It's not succeeded yet in a controlled system, as far as I know. It may have in some places and been suppressed, but I doubt. It is being investigated at enormous expense in many parts of the world by a single country or groups of countries, and it is the hope of the future. It could be clean, and it could be unlimited. It's very important for your great-great-grandchildren when other fuels have run out and we have only one remaining supply, if we're not careful, which will be the greatest nuclear reactor of all, the sun. Sunshine is the product of a nuclear reactor. Fusion could come. It's very difficult to arrange. You have to drive the elements together against tremendous repulsions. You've got to raise the system to 50 million degrees in a centigrade scale or even more, and then on top of that you've got to contain the products so they don't get lost, fly out. It's a very difficult problem, but it's worth tremendous research and care to find out. That's the hope of the future. I want to switch now to something entirely different. I want to switch, for a special reason, which I must tell you at once, to waves. The reason is this, that we want to build a wave model for atoms. Otherwise, it won't be clear why the old Bohr model didn't collapse. And therefore, we're going to look at waves. And first of all, I would like to have two simple waves like this. This is purely a teaching model. And we're going to have this, and I'm going to ask if that is how it will show easily on the monitors around. Is that good? Then I'm going round in the front. These are two sources of waves. So the wave comes out flip-flap, 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 flip-flap along to there, flip-flap, flip-flap along to there. And therefore we get here a wave arriving here on a screen, making something here go flip-flap, flip-flap, and the other wave making something go flip-flap, flip-flap, so they both go together, flip-flap, flip-flap, flip-flap. But if we now move off the axis, somebody must just put a restraining hand on the two sources. I put them a little bit further apart and then hold them there, if you will. Thank you. Now if we go round to here, what happens when we get round to there? Again, we have flip-flap together a lot. But when we go part way, when we get just about to there like that, what's happening? This one is going flip-flap, and what's the other one doing? Flap-flip. Flip-flap and flap-flip make nothing. This is called interference of waves. It's one of the stupidest names I know in science, because it's exactly what they don't do. They leave each other alone, they don't interfere, but they do add up, plus and minus like algebra. And so now we have flip-flap together, flip-flap and flap-flip, 0, flip-flap together, and again 0 there. And so we get places of bright effect from waves, no effect, bright effect, no effect. That's just a model to explain what I'm going to show you about two lots of waves coming out from two supplies. This could go away, and we're now going to show you real waves, ripples on water, was one of the finest ripple tanks I've ever seen. Mr. Coates has a ripple tank with one vibrator driving ripples, which you'll see in a moment on the screen. They're coming out from a source here where my hand is. Can you see the ripples spreading out, round ripples? And now he's going to make another source operate as well, just as I did with the two curves there. Let's have two lots of ripples, please. In a moment he'll turn on a second source as well. It's quite a trick to do. When he is ready, there, look at that. We saw it for a moment. There. Now can you see what's happening? Can you see regions, if you half close your eyes, blink your eyes for a moment, it may help. Can you see regions where you get nothing and regions where you get a lot like that? You get some regions of flip-flap together and some regions of flap-flip and flip-flap where there is nothing. That is an interference pattern from two sources, and that's characteristic of waves. They make bright places and dull places when they combine together like that. Thank you very much for that, Mr. Coates. It's quite a trick to make it so clear. I would like you now to make another model for me, please, another experiment of pushing light through a grating. We're going to have light coming in, and I think I better have a nice bright color for that. Here is light coming in to a slab of glass, which is going to have something curious done to it. Here is the slab of glass. It's going to have a plowed field effect of little channels ruled in it, so that the light comes through it unevenly from each of the plowed channels in turn. Or perhaps it would be easier if I drew it as a row of slits like that, so that you had light coming through this slit and that slit and that slit, or through this ploughing furrow and this ploughing furrow and this one like that. But it doesn't come straight through only. It comes also out in this direction, out in that direction, out in that direction. When it does that, the extra path for one lot of light compared with its neighbor, there's the extra path, there's the extra path. We're going to do that in a larger picture for you now, like this. There is, oh, I'm sorry. Here is a slit, and a slit, and a slit, and light could come, of course, straight through. It could come through like that, like that, like that, but it also could come out in this direction like that, and like that. And the extra path is what I'm going to show you in a reddish color, like that. There it is. That's the extra path. That's the extra path. And if that is one wavelength or two wavelengths, then you would get all these adding up together, flip-flap, 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 in a strange direction. Mr. Coates now has that ready to show you. He has such a grating, as it's called. It's a plowed field, and as the lights go lower and lower, you will see much of the light goes straight through where my finger is, but out to each side, light is swung to one side, and you see a spectrum. The red slung further out, longer wavelength than the blue, which is not slung out so much. You might see, if you look very carefully, not only one sling out for all those colors, but a double sling out and a treble further out, but it's very faint. We can easily come over the faintness, though, overcome the faintness, with another experiment. Mr. Coates has here a laser which is making a beautiful red spot. Here, as the lights go down, you will see the red spot passed through a grid of wires. Look at that, for a beautiful spreading out into spots. That is, each spot shows a different swing out by the grid of wires, and it's characteristic of waves. Waves can do that when they go through a grid of mesh like that, and that is characteristic of waves, and we want you to know that it is. So that having seen what waves of light with a laser can do, I'm going to point out that you cannot expect to do that. You cannot expect to do that with sand. If I pour sand through a sieve, it will make a beautiful mountain of sand below on the paper, but it will not make spots in a regular pattern. There's no chance of it whatever. That's what happens if light could only consist of knobs. You would not have any kind of pattern of spots. But we know something which does consist of knobs: electrons. They're little bullets. And yet Mr. Coates is focusing a beam of electrons through a crystal of carbon, very thin. It's a beautiful apparatus, arrived from America to be presented to the Royal Institution, and you're going to see that electrons passing through a thin crystal can make a pattern of spots. As the lights come down, you will see the pattern of spots there. If Mr. Coates puts his finger on the central white thing there, he's obscured that. Can you see a sort of hexagonal pattern of bright spots? Those are made by electrons coming through to the screen of an oscilloscope tube, just like the ones you know, except that halfway down the line of electrons there is this thin crystal which is swinging the electron beam apart. Electrons can make waves. They do have a wavy behavior. Somebody once said electrons are waves on Monday and Wednesday, spots of bullets of energy on Tuesday and Thursday. I don't think that's true. Which way they behave depends on the question you ask. Ask an electron his wavelength, he'll reply to you in a wavy way. Ask him his energy, he'll reply to you with a bullet-like knob like that. I want now to show you quickly some wave models. We have a wave model of a string, and we're going to drive the string with a vibrating tuning fork, a giant there, up and down. If we drive it at the right rate, you will see it makes the string make what we call a standing wave. Here we have one loop going flip-flap, another flap-flip, flip-flap. This is a stationary or standing wave. Now look at it with flashes of the right frequency, and you'll see what the string is doing among that. Can you see it going apparently slowly up and slowly down and up on the next loop here? It's an old experiment, but it's a delight to see. There you are. If you don't enjoy that, you're inhuman. Right. I want to go straight on to another illustration of a wave, because that's a rather difficult wave to put into an atom. You'd have to join the two ends in a great round belt, like any belt of a snake eating its own tail. Mr. Coates has a very nice illustration here, which he will show you quickly. This is a nucleus and a round electron orbit, no longer true, but nice to see, because this is halfway between a Bohr orbit pattern and the most modern mathematical wave pattern for atoms. You see it vibrating, the round ring vibrating in several complete half loops, so that it is a pattern which can stay stable, and that's why atoms don't collapse, because their electron control orbits are complete sets of loops, the equivalent of that. I want to change now to quite a different discussion. How do we know about electrons? How do we know about atoms? Suppose we say that atoms are round things. Once people think an atom is a round ball, like a cricket ball. And they ask, what's the size of it? Which is very unreliable. And therefore, we have to have a warning against believing these descriptions too strongly. We only use the statement that an atom is round as a way of explaining something about its symmetry. I want to issue my warning by doing a measurement. I would like to be able to measure my average diameter. It's all right. Oh, but we'll use this. I'd like to measure my average diameter like this. There it is. There's my tape measure around me. Take it off. And what do we divide by to get the diameter? Oh, no. Rough work. This is a rough game. Divide by how much? 3. 3's near enough. There's my diameter, like that. But is it always so? It depends on how I make the measurement. I'm going to show you. You never know what you find in a cupboard in the Royal Institution. We can do the same thing here. We can do that, get the same diameter. But instead, if I use a cheese wire, then the diameter is extremely small. And the diameter is extremely small. It's that much for a cheese wire, just something like that. It depends on how you make your measurement. So now we want to give you another warning, please. We want to show you how you view something and attach it too easily to what you already know. We have a house that's coming in. It's a large room. As soon as they're ready, the camera will look into the room. He'll look across. At the far end from where the camera is, there are 2 windows. And you will see them. Oh, look, there's something there in one window. Look, there's a doll in the window there. Can you see the doll? Now move the doll, please. Move the doll to the other window. Is it the same doll? Move it back. Move it back again. We'll ask the young lady to have a look herself. Look through the window yourself. And the other window. Well, how can she grow and shrink like that? It's amazing that that can happen. And yet, to you and me, it's a perfectly respectable room. Camera, can you see the floor at all? You see, there you are, a beautiful floor as well. Now let us open the room, open the front of the room, and see the truth. There isn't any truth for atoms. I don't know what that means. But in this big model, you can see what really is there. And you might be quite surprised. This is because when you see something new, any adult, any growing child attaches the new thing to old information. Just look at that. Can you see it? The camera is going to look. Oh, we need you. Climb in, walk about in it. Never mind if you slip up. Look at the ceiling, point to the ceiling, low ceiling, high ceiling. Look at the floor, look at the windows as they really are. And all that was because you looked through a peephole which deceived you. There's the truth, but I don't know how to do the truth for atoms. I just warn you, if we say an atom is a round ball, we will never know if it is a round ball or not. It's just our method of describing it. Thank you very much. Be warned, be warned, be warned. Be warned of the danger of jumping to a conclusion with old things. But one difficult question. How does a baby see? Baby has no collection of old knowledge to attach the new, strange knowledge to. A baby has a much harder business of learning. And now at last we shall come to the promise that you shall see atoms on your own. As we do, I will point out that we now think of atoms as having a wavy pattern to control their patterns. We have probable guessing of where parts of the atom are. This fuzzy thing is the electron cloud. Here, due to our wavy prediction, is the atom of hydrogen with the most likely place for the electron of all places at the center. When it's more excited, other orbits. That's a warning of the future. And now here is the new experiment we're going to show you. We're going to show you a flask like this, in which in here, where I'm putting my pen, there is a very sharp tungsten point. It's very, very small. It's so small that compared under a microscope with a sewing pin, dressmaking pin, there's the pin and here's the needle. It's a very fine needle of tungsten with only a dozen atoms or so on the front. And here it's just placed there. Below it is a ring, positively charged, negatively charged point, huge electric field, driving electrons straight off the corners of the point wherever it's most strongly curved, and driving through the ring and hitting a photographic film below. You can see the small picture of the same thing there, magnified needle, still more magnified, and finally a whole bunch of tungsten atoms like that with corner ones in the layers which hurl away electrons or hurl away whatever else we put there. In the modern version, we put helium atoms there, make the needle positive and the hook negative. Nowadays, we do that, but earlier we used for that electrons, and we shall show you the earlier model. Somewhere far away, they made a model of cork fishermen's floats for that. They painted them with ultraviolet fluorescent paint at the corner ones. I have here our model, which has proceeded only so far, and we're going to look at that with ultraviolet light. As the lights go down, you will see the green glow. Can you see them glowing? Just a few ones which are at corners where the electric field, like the sharp point with the smoke, is very strong. And now let us look at what you see with a real tungsten needle. There's a rough photograph of it. And here is a detailed photograph. Every white spot is an actual atom in that, of layers of atoms, particularly the corner ones on tungsten needle. In the photograph you're seeing atoms, but I would not cheat you. You shall see the real thing. We'll use electrons, please. Are you ready, Mr. Coates? He has to, first of all, clean up the tungsten needle inside that tube. He must grill off with a little glowing filament a few foreigners that have got onto the tungsten needle end, foreign atoms of other things, and then the glow will soon clean it up. You may see the filament glowing up on the monitor, and then he will turn that down and apply a very strong electric field between the tungsten point and a neighboring place, so that there's an intense dragging force dragging electrons off. Positive elsewhere, negative on the point of the tungsten, dragging electrons off the most draggable places where they are at corners or edges. And then you're going to see, wait, lights right down. Those patterns are patterns of single electrons showing where the single atoms are, floods of electron from each significant atom. Can you see the pattern? Can you see it flickering a little bit? Those are the corner places. You are seeing atoms. But we can even let a foreign tour visit the tungsten point, a whole group of barium tourists. Barium is another element, and barium atoms can be grilled off a side tube Mr. Coates is doing that now.
cleaning the tip.
He's cleaning the tip of general foreign visitors, so he has only a barium troop arriving, and you may see them crawling about on top of the tungsten tip. It'll be very quick, and you'll have to wait till it's quite dark, and you see it suddenly happening. Suddenly happening. You're ready with the barium? No, he's not. He's heating it up. He's arranging to produce the barium. He's getting it ready, and when the lights go down, you may see it very suddenly when he grinds his Van de Graaff machine to apply the huge voltage. Now watch. It's going to happen. Quick, watch quickly. Can you see some strange crawlers flickering around? Whole bunch of tourists. Go on, go on, go on. You are seeing atoms round those patches of tungsten covered with barium creeping about on top of it.
Coming back to tungsten now.
Now we're getting back to plain tungsten. Thank you. In that sense of what you know about electric fields, about the Van de Graaff machine, about sharp points, about electrons. It's electrons making the pattern there as they're hurled out from the edges of the atom layers. In that sense of all you know, you may believe that indirectly, in a way indirectly, you have seen atoms. And now, I wish you well. You have seen experiments, you have heard arguments, you've gathered some information, and it is with you to put them all together. If you put them together, you will see that for your knowledge of science, it's necessary to see experiments. There was a great French mathematician who contributed much to physics, but he did say in the preface to one of his books, the British are very strange. They do experiments and rely upon them. All right? We're strange here, and we enjoy being strange and doing experiments. If you share our enjoyment, and you like to hear a scientist talking to other scientists, then indeed you are part of the new generation ready for the new world, which will be a world of scientific interests. Within your lifetime, you may see fusion reactors put into play, instead of only a hydrogen bomb, which is a too fast fusion event. If in your own life, whether a scientist or not, you can say to yourself, your parents, your brothers and friends, science is interesting experimenting and clever arguing. Then if you can do that, the new age of science will, with you, have come true. It will be a satisfaction to you, and I hope a delight for all your lives. You have my blessing.